right. So this is the second question, okay, and here they are asking to show that e raised to iax equal to cos x I plus I sin x a. This I is the imaginary, and they have given one more condition, that is a square equal to I. Okay, so if you want to derive this, we need this McLaren series. This is a e raised to x expansion, that is the summation x power n by n factorial, where n equal to 0 to infinity. If I substitute these n values, this expansion can be taken as 1 plus x square by 2 factorial plus x cube by 3 factorial plus x power 4 by 4 factorial, so on. Now we want to find this, okay, so I'm taking in the place of x iax, imaginary term. So then it is e raised to iax equal to, and one more thing you have to remember, whenever there is an operator or matrix in that expansion, this 1 is nothing but I, which is identity matrix or identity operator. Just substitute x value, that is iax plus iax whole square by 2 factorial. Let me substitute. So if you want to write a few more terms, you can write. Now they have given one condition, that is a square equal to I, identity. So from this we can write a cube. If you take a cube, which is nothing but a square into a, so that's why this is again a. So finally we can conclude, if you have whole power even number, that is a power n, so we can take it as I if n is even and n is odd. Fine. So by using this, again I am going to simplify. So e raised to iax equal to identity plus iax. Next one, I square, so which is nothing but minus 1. So minus a square is nothing but I, identity. Next x square by 2 factorial. Next term I cube is there, so I cube minus I, and a cube, which is nothing but a, x cube by 3 factorial. So if you want, you can write another two terms. Now I am going to take a common, okay, so here I is common, then I will get 1 minus x square by 2 factorial. If you proceed a few more terms, you will get x power 4 by 4 factorial, right? And the next plus I am taking common, then I will get x minus x cube by 3 factorial and plus x power 5 by 5 factorial, so on, right? So this is nothing but expansion, cos x expansion, McLaren series again, and this is the expansion of a sine. So finally we can write e raised to iax equal to this I identity cos x plus ia sin x. So this one, if you rewrite this, you will get the form whatever they are asking. So e raised to iax equal to cos x to I plus I sin x into a, right? So we can derive this in a different, another way also, that is by using a spectral decomposition. So here we have taken McLaren series. Next, let us take a spectral decomposition. Here we can derive the same thing by using spectral decomposition. Right. So what is this, a spectral decomposition? Now, whenever you know the eigenvalues and eigenvectors of a corresponding operator, so right. So if you know the eigenvalues and eigenvectors of a corresponding operator. So we can write this as spectral decomposition form. Let us say A is a operator or a matrix whose eigenvalues are lambda 1 and lambda 2, eigenvectors are psi 1 and psi 2. Then we can write this as lambda 1 and the corresponding outer product, that is the eigenvector, corresponding eigenvector outer product, plus lambda 2, the outer product of the eigenvector corresponding to the eigenvalue lambda 2. Right. So here they have given one thing, that is a square equal to I. If I take the characteristic equation, that is a Cayley-Hamilton theorem, if you take lambda square equal to 1, which gives lambda square, uh, which gives lambda equal to plus or minus 1. So finally we got the eigenvalues are plus or minus 1. Eigenvectors no need to find, just leave it. So according to this, I can write the given matrix A as psi 1 outer product minus the outer product psi 2, because we got the eigenvalues plus or minus 1. So leave it. Now here we are going to write e raised to IAX. Remember, if an operator A is having eigenvalues lambda 1 and lambda 2, eigenvectors psi 1 and psi 2, then e raised to A operator, eigenvalues may change but eigenvectors remains same. So according to this spectral decomposition, we can write this as e raised to I lambda x, eigenvectors are same, that's why I'm taking same psi 1 outer product plus e raised to I lambda 2, this is a lambda 1 and lambda 2 x psi 2 psi 2. Already you know what are lambda 1 and lambda 2, just substitute, that is e raised to Ix psi 1 outer product plus e raised to minus Ix outer product psi 2. Okay, so now I think we can write this as by using this de Moivre's theorem, cos x plus I sin x, and this is nothing but cos x minus I sin x. Okay, so now if I take common or something, then I will get cos x. First I will get a common cos x, and after that here I have outer product of psi 1 and plus here again cos x term is there, so I will get the outer product psi 2. Next after that I am taking a plus I common, okay, and sin x also common. Then if I take sin x common, here I will get the outer product psi 1, and since this is because of here minus sign, okay, so here I will get minus psi 2 outer product. Now if you observe carefully, this is nothing but the outer product form of A, so I can take it as A. And if you see this one, eigenvalues are 1 1, okay, so this is nothing but identity matrix. Remember, the outer product form of identity matrix is that psi 1 outer product plus psi 2 outer product. So finally I got cos x I plus I sin x into A. This is nothing but e raised to IAX. Okay, so this is another way of simplifying, deriving by using a spectral decomposition. So again in the same problem, they are asking to verify the equations, this 4.4 to 4.6. Okay, so what are these? They are asking to find the Rx of theta. This is the rotational matrix about x-axis, that is e raised to minus I theta by 2 x. Here this x is nothing but a Pauli spin matrix. Okay, so already we got this relation, that is e raised to plus or minus Iax equal to cos x I plus or minus I sin x A. So this can be written as cos theta by 2. In the place of x we have theta by 2, I identity, minus I sine theta by 2 into A. In the place of A we have Pauli spin matrix X. If I substitute this, if I substitute this identity matrix, which is 1 0 0 1, and Pauli X matrix 0 1 1 0, if you substitute here, then you will get this cos theta by 2 and minus I sine theta by 2, and here also minus I sine theta by 2, and this one cos theta by 2. So this is the rotational matrix about x-axis through an angle theta. Okay, and here the next one, this is again cos theta by 2 identity, minus I sine theta by 2 y. So here you can substitute the Pauli y matrix, that is y equal to 0 minus I 0. If you substitute this, you will get here, this is a cos theta by 2, cos theta by 2, and minus a sine theta by 2, and sine theta by 2, cos theta by 2. Next, z. Okay, so here similarly, this is a cos theta by 2 I minus I sine theta by 2 z. So if you take the Pauli spin matrix z, which is 1 0 0 minus 1, and if you substitute here, you will get e raised to minus I theta by 2 0 0 e raised to I theta by 2. So these are very important while we are constructing this quantum gates. These are the rotational operators, rotational gates along x-axis and y and z. So please remember these matrices. Okay, thank you.